Welcome to CPE350 Chapter 6, the second introductory lecture in which we cover example 10, evaluating the critical radius of insulation for a pipe. The problem we're given is a pipe with hot water, an outer radius of copper coated in insulation of fiberglass, and the room temperature is ambient at about 30 degrees C, and we're asked to calculate the heat losses from this hot water pipe. This should be a flashback from Chapter 2. In Chapter 2, we were looking at almost the same example, except we were neglecting the transfer resistance between the outer surface of the pipe and the ambient air. Basically, we were neglecting convection because we hadn't covered it yet. So this example is going to compare the effects of convection to neglecting those effects of convection. All right, onward. Here's the physical schematic of our scenario. We've labeled the radii that we know, the inner radius and outer radius of copper, and the radius of the fiberglass is RFG. We're given a couple of our constants in the statement of the problem, and some of them we have to look up. You might be able to find different values for these parameters. That is absolutely fine. We're just trying to get an order of magnitude estimate here. So we're going to use our generic expression for heat flow in a multi-layered geometry, and we're going to write out the terms of resistance that we need to calculate. So there's the convection between the hot water and the copper, conduction through the copper, conduction through the fiberglass, and finally convection from the air, from the fiberglass into the air. And when we write these carefully using the form for cylinders, we've got our two convection terms and our two conduction terms, and then we can substitute in the values that we have for these variables and calculate the actual thermal resistance for each layer in this system. We note that we don't know the length of the copper pipe. It's not specified in the problem. So we multiply both sides of the resistance by that length so that we can calculate this composite variable, LR total, which will eventually come out. So we look at the resistance due to water, convection, and conduction through the copper, and both of these are pretty negligible. You could pretty much omit them from the problem. It's only the conduction through fiberglass and the convection of heat from the fiberglass into the air that actually significantly affects the thermal resistance to heat transfer. So we plug in, we've got an actual value here. We plug it into our heat flow equation, first multiplying both sides by 1 over L so that we can obtain the quantity we've calculated, LR total. When we plug in the numbers, we get a significantly lower value of heat losses than we did in Chapter 2, which was on the order of 50 watts per meter, just because including the effects of convection is significant. It's a significant barrier to heat transport. So that's the first part of our answer. The second part of our answer is to remove the insulation and recalculate what this rate of heat loss would be. So we do that and we can write the thermal resistances. This time there is no conduction through fiberglass because there's no fiberglass, and that means that the radius at which convection occurs is the outer radius of the copper, which is our O, which I've highlighted in red because it's a slight difference from our previous convection expression. Again, plugging in the numbers, we see that convection from air dominates, and we can calculate the actual heat transfer with no insulation. Great, we're done, almost, except that if we compare this value with no insulation to the value with insulation, we see that we're in this scenario where insulation is actually increasing the rate of heat losses. And this should not make sense. This is very strange, right? It is absolutely correct. It's mathematically correct. It's physically correct. And to explore this phenomenon, we're going to introduce the idea of a critical radius of insulation. And anything below the critical radius is going to actually increase your heat losses. And basically this comes about because our heat losses due to convection increase as the insulation increases in thickness because there's just more surface area from which heat can be lost. And so we see that linear increase. At the same time, the heat losses due to conduction through the insulation decrease as the thickness of insulation increases. Whenever you have two trends that are moving in opposite directions, any quantity that involves their sum is likely to have either a minimum or a maximum. And in this case, we're looking for the maximum in heat transfer rate so that we can find the minimum critical radius of insulation. Again, our conductivity is depending hyperbolically on the radius of fiberglass insulation, whereas our convective resistance depends linearly. And so that linear dependence is a little bit slower in this instance to rise than the conductive resistance drops off. And so that's why you eventually get to the point where insulation begins to reduce your heat losses. Okay, so what we need is to calculate the value of this critical radius in order to prevent under insulating our pipe. And so to do that, we're going to look at the derivative of our heat term with respect to the radius of insulation. And we're going to say at this critical value of the radius, the heat loss is a maximum. And we want to know what that maximum heat loss is because that's going to correspond to the minimum value of insulation thickness that we can apply. So that's the equation we'll use to get there. Just a reminder, we already know what QR over L is. It's this rather large expression, which I've written the thermal resistance in brackets to the power -1, because it's going to make it just slightly easier to differentiate the expression. And when we differentiate with respect to our variable, which is the radius of fiberglass, everything else is a constant. The first thing we do is multiply the quantity in square brackets by -1 and raise it to the power -2. And then we have to multiply that quantity by square brackets by its derivative with respect to RFG. The first two terms do not contain RFG, so they go away. We've got a logarithmic term, which it's a quotient, and so you can write that third term in brackets as the natural log of RFG minus the natural log of R outer, both over the constants. And so you can see that the R outer term goes away because it doesn't contain a fiberglass radius variable. So we get one derivative term from the logarithmic term, and from the last term, our convective term in air, we also have the radius of fiberglass raised to the power -1. So we multiply by -1, raise it to the power -2, and that's our derivative. Okay, so to plug this into our expression for the critical radius, we're going to call the critical radius RFGC. We don't know what its value is yet, but we know that when we plug in for that value, the entire derivative is going to be 0. And that's what this expression says. We have a choice. We can divide both sides by either the top term or the bottom term. The top term is a little bit messier, so I'm going to divide both sides by the top term, getting rid of that effectively, and I'm left with the bottom term equal to 0. So now I can rearrange this, cross out one of the RFGCs, cross out the 2 pi, rearrange and solve for this critical radius of insulation, which is just the thermal conductivity of the fiberglass over the heat transfer coefficient of the fluid. And this is a very general solution for any insulated cylinder. The answer will change just a little bit for like a slab geometry or a sphere geometry. So finally, to calculate the critical radius of fiberglass insulation for our particular problem, we plug in the numbers and we get 4 centimeters. And this is why when we apply 0.5 centimeter of insulation, which is less than that critical radius of 4 centimeters, we increase the heat losses. And then if you wanted to recalculate the problem for any value greater than 4 centimeters, try 4.1 say, you'll see that you begin to decrease the rate of heat loss with respect to the uninsulated case. So I hope you've enjoyed this problem, and I'll see you for the next section.